keep them to the end. Our next speaker is Poulos. Foundation, an impressive record. I think that everyone has the idea that if you have a good foundation, you need a good foundation, you have to get someone from down under.
Thank you very much, Chairman, and good morning or good afternoon. It's still good morning, ladies and gentlemen. I'm going to talk about an issue that has been mentioned fairly infrequently in this conference, and yet it's a critical issue for all tall buildings, and that is foundation design and the testing of the foundation elements. And I do this on behalf of my co-authors, Ahmad Abdul-Razak, Francis Badelow, and Sung-Ho Kim. I'll talk a little bit about the ground conditions for this project, which is here just outside of Seoul in Incheon, the procedure that we adopted for foundation design. I'll tell you a little bit about the design studies in the detailed phase and the pile load test program and how those results compared with our design assumptions. This is the rendering of the project. It's to be a 600-metre tall, 151-storey building. Coffey and Jin Young were jointly the geotechnical designers. Thornton Tomasetti were the structural engineers, and the architects John Portman. And this is what it looked like about 3 years ago. It's basically, at that stage, was out in the water. This is on reclaimed land. So this adds another element of geotechnical excitement to the project. And in terms of the steps that we followed during the design process, we did a desk study first, as one usually does. There was a detailed site investigation program to look at the stratigraphy and the variation of ground conditions over the site. There was a series of in situ and laboratory testing carried out, then a preliminary assessment of the foundation requirements, refinement of the design, then detailed design, and then in situ foundation testing. And so, sorry, let me go back. So we are actually, at this stage, we still have to monitor building performance on the assumption that the building will actually proceed. The ground conditions were identified with 23 boreholes, which went to depths of over 100 metres. There was a lot of in situ testing done, including geophysical testing, a lot of laboratory testing done to characterise the rock, and we had a lot of engineering geological input into this because this site, as it turned out, was a fairly complex one. And at the end, we developed a geotechnical model for the site, parameters for the foundation design. And what made this site complex was that it was discovered that there was actually a sheared and crushed and faulted zone right in the middle of the site. There was essentially marine deposits here, and then there was weathered rock, and then other less weathered rock called soft rock actually here. But in the middle of all of this was a very complex sheared and faulted zone, and that created some difficulties. The other issue here, these are actually contours of the depth to the bedrock, and they varied by about 20 to 30 metres over the site, so that this was not a nice level site. It was rather complex. In terms of the issues that we had to deal with in the foundation design, the first and obviously foremost was ultimate capacity and overall stability. We also, in conjunction with that, had to check for cyclic loading effects due to wind and seismic loading to see whether that would have any influence on the capacity of the foundation system. Settlement and differential settlement, critical issues always. We needed to worry about external ground movement effects due to the reclamation fill and the effect it would have on the overlying marine sediments. We looked at the dynamic behaviour of the foundation system under wind loading, earthquake response, and the potential for liquefaction, and of course we had to consider the structural strength of the foundation elements, which we did in conjunction with our structural colleagues, and durability. All of these were fairly critical issues. There were basically 3 stages in the foundation design procedure. At the concept and schematic stage, we estimated pile capacities and looked at various foundation layouts. In the detailed design phase, the loadings were finalised and we went through analyses of ultimate limit state and serviceability limit state conditions. And the post-design studies involved the pile load testing. In terms of the detailed design, when we looked at this, there are 2 essential components, and we used limit state design approaches here. We looked firstly at the ultimate limit state, the overall stability and the cyclic loading effects, and then with respect to serviceability limit state, in other words, the settlement and normal operational conditions, we looked at settlement and differential settlement, the stiffness of the pile groups, the responses of the piles under vertical and lateral load, and then we did a detailed 3-dimensional analysis to check the foundation design. A number of key parameters that we had to decide on, the shaft friction and end bearing ultimate values for the piles, the soil stiffness so that we could estimate movements, ultimate lateral pressures, the soil stiffness for lateral loading, which can be different from that for vertical loading, and also dynamic soil stiffness and damping. This is typical of a model that we developed with the marine deposits, the weathered soil and rock, and then the so-called soft rock. This was one of 8 models that we used on the site. We had to divide the site up into 8 zones. Each of these had similar components but different depths, reflecting the different depth to bedrock. The actual foundation system we came up with, 172 piles, so quite substantial, 2.5 metres in diameter, and founded a minimum of 2 pile diameters, 5 metres, into that soft rock layer, or if not, then the founding depth was below elevation minus 50. The mat was relatively thick at 5.5 metres. And this is what the actual layout looked like. Basically 4 wings and a central rectangular component. That layout was developed in conjunction with the structural designers. Now, in terms of the ultimate limit state, and forgive me for the equations, I'm an ex-academic and I can't help myself, but basically the criterion was that the factored down geotechnical capacity had to exceed the factored up load combinations. So this is the basis of ultimate limit state design, and we used reduction factors for our estimated capacities, a different factor, 0.65 for axial load than for lateral load, 0.4, just reflecting the greater degree of uncertainty for lateral response. And indeed, when we did the ultimate limit state analysis, running it through a nonlinear pile group analysis program, we found that configuration to be quite stable. The cyclic loading effects, this is another criterion that we've introduced because we are concerned that with piles that rely, at least to some extent, on friction for their resistance, you need to make sure that the cyclic loading component of the load on those piles does not exceed a certain value which might cause degradation or fatigue, if you like, of the pile resistance. And so our criterion here was that we needed the cyclic component of load to be less than about half the ultimate shaft resistance. And with that, there would be very little risk of cyclic degradation of skin friction. And for every pile in the group from our analyses, we worked out what the maximum component of cyclic load was, and it satisfied the criteria. With serviceability, we applied these serviceability load combinations. And we got settlements of the order of 60 some millimetres, and we used two different approaches, an in-house program called GARP, and then a three-dimensional finite element analysis, and we got rather similar results, which was pleasing. Just one word here. It's important that we recognise that when you have a large group of piles, these piles interact and they actually cause a reduction in the stiffness of each of the individual piles because of interaction through the soil. And in this case, the individual piles had stiffnesses in the order of 3,500, whereas the average group stiffness was less than 700. So there was a factor of a little more than 5 because of the group effect, and it's important that this be taken into account by the structural engineers in doing their final design. We can also, from this, get the distribution of pile loads, as we show here. This is the three-dimensional finite element. It doesn't show the whole model, but that's how we characterise this. And this is another structural model that was carried out, putting as piles springs which we provided the stiffnesses for from our geotechnical analyses. So in the end, this is the sort of model that gives you the final design bending moments and so on for the various foundation and structural components. The post-design studies, there were a number of load tests carried out. This is the site of those load tests. They were carried out using an Osterberg cell test, which is a very nice test that's been developed over the past 20 years, which is essentially self-reacting, and you can put very large loads on. You can load the base up to failure, to the ultimate. You can load the shaft up to the ultimate, and it really does give you a lot of information. So I won't go into detail on this because time is running away, but basically, just to summarise the results, what we have here are the design values that we adopted for the soft rock and for the weathered rock. This is the material above that. 4 meganewtons, 4 megapascals allowable end bearing, 350 allowable skin friction, and 250 allowable skin friction in the weathered material. We got almost twice that. As an average for the load tests. The only one that actually wasn't in excess was one of these test piles here. But basically, the test piles performed better than we had expected. We also did lateral load tests where we pushed one pile against an adjacent pile. Here is what it looked like, and you just have a jack between these two and you measure the lateral deflections as you increase the loads. And again, I'm sorry, this has gone a little bit out of sequence, but our design had values somewhere between 120 and 86. For static loading, these values were in fact, again, about twice as large in the maximum, and the dynamic values were actually significantly greater than that. So in conclusions, we have here a site where there's complex geology, and it's critical that in any project like this that we understand the geology and the constraints that it imposes on us. We used here different ground models for different parts of the site. We used a 3-phase design process and we did detailed analyses during detailed design, but we always checked the results with simpler methods because one has to be careful in a complex analysis that you're still getting results that are meaningful. The load test program was very beneficial because it showed us that the results are more favourable than we anticipated, so there is a potential then to modify and economise on the design. And finally and critically, I think this is an example once again of the essential nature of cooperation between geotechnical and structural designers. We, as the geotechnical components, provided pile stiffness values for the structural engineers to put into their program, and what is critical here is that those stiffness values incorporated the geotechnical interaction of the foundation system. Thank you very much.
Thank you very much, Harry Poulos. I'm sorry to rush through, and I'm sure you should have had more time. The next speaker is Rati